Hello. I'm Charles. I'm actually subbing in for our security engineer, who is going to present a different talk, but then he got sick, and so I am giving my own talk, which is also on differential fuzzing, but it's about ABI decoding. So first of all, why does that, show of hands, who knows what ABI decoding is? Okay, great. ABI decoding is extremely hot in the compiler. You probably don't think about it much, but whenever contracts call each other on the EVM, they follow a standard called ABI encoding and decoding. It's a serialization format, along with some other things, metadata and stuff. But anyways, excuse me. ABI decoding is the part where you decode data that's been encoded by another contract or in call data or maybe in code or data somewhere, and you want to basically deserialize it into your own local memory structures. And there's something that's very interesting about how ABI decoding works. So the ABI spec defines two kinds of data. One is static data, so that's stuff whose length is known statically. So for example, a uint 256. Everybody knows it's always going to be 32 bytes. And then there's dynamic data. For example, a bytes type, which has dynamic length. It's variable at runtime, basically. So the way that the ABI defines the data layout is it puts all the static data in one section, and then where there's dynamic data, it includes pointers to what's called the dynamic section. So for example, if we have some bytes, this is a tuple of bytes, by the way. So because it's a tuple, the ABI defines one static field, which is the location of the bytes data in the dynamic section. And then it has the dynamic section, which is kind of a reasonable encoding of bytes, which is the length word and then the data. A more complicated example is a tuple of bytes. It's recursively defined here. And because I'm able to use the formatting with the bullets, you can see the recursive structure, actually. So you have the static section of the outer tuple. It points to this dynamic section. So the inner tuple of bytes is defined as a dynamic data structure. And then you have this thing, which is the static section of the inner tuple. And then that points, again, into the dynamic section of the bytes. The dynamic section of the inner tuple, which is the bytes. And then you have the bytes data. So why is ABI decoding hard? So this is from the ABI spec, the Solidity docs. And this is how it defines how to write a decoder. And you'll notice that it doesn't really say how to write it. It says you could have a strict decoder, which basically expects the data to be encoded in the way that this canonical encoder that I just kind of outlined. Or you could be a little bit less smart, and then everywhere you see a pointer in the static section, you just follow it. And so you don't check if the pointers are valid. You just kind of keep following them. And we'll find out why this is kind of problematic in a minute. But why is this a useful property? The useful property is that sometimes people like to have kind of clever encodings of their data. So here's an example of like a tuple of 2 bytes. And this user is very clever. And because the data is duplicated, you only need to write out OX1234 one time. And then in the static section, where you have the pointers to the bytes data, they point to the same location in the dynamic section. And so it's kind of like aliasing. So you can define very clever or interesting structures. I'm getting looks from the audience. Where you don't really encode it in like the obvious recursive way, which is like encode this, then encode this, then encode this. You can have like weird pointers in, out, up, around in the payload. The other reason why this is a useful property is because the implementation can be more efficient if you don't actually check that the data encoded is like super strict, like each element is followed contiguously by the next element and so on. You can do, again, what I just said, which is like follow the pointers. So we've had this implementation of just like following the pointers for a long time. And this was reported as a bug by Alex Wade a long time ago, which is that when you decode stuff from call data, or when Vyper decodes stuff from call data, we don't check that the pointers are valid. And this is like maybe a problem because like here, where we have, yeah, this is a simple example. Here, this pointer could be invalid. It could be like OX 1,000,000. And then when you jump to that pointer or to the data where that points, you just like get a bunch of zeros in the call data. So at the time we analyzed this and closed it because call data is always user controlled. So like even if you can force the compiler to like read like some pointer where it doesn't exactly expect, you can't really do anything because it's just pointing to data that you also provided. So it's not really an issue. So when this starts to become a problem is when we implemented the ABI decode built-in. So ABI decode is a user facing function that ABI decodes a buffer of data. And the difference between this ABI decode and the built-in call data decoder is that this operates on memory. So this is a very interesting bug because, oh, you can't actually see the, I wonder if I can open this actually. You can't see the Y, which breaks this. Oh, yes, excellent. So this is the call data which breaks it. And basically, you convince it to read data from OX60, which is outside of the payload, outside of the Y buffer. So the way that these are laid out, basically, you can force it to read data from outside of Y, which in this case, we mutate it in between the invocations to ABI decode. So that's a kind of weird thing, right? That's pretty uncommon. Oops, how do we open this again? Control F5, is it? Oops. Whoa. Okay. Okay, so that's kind of weird. And this is what's called a talk to, apparently. So basically, if you can convince the user to like, it's time of check versus time of use. So if you can convince like some poor developer to write some code that ABI decodes the same data, in between there's another memory write, then there's like this weird bug. Okay, so this is like just the start of the journey. So then we like started to fix this bug. And these are some commit messages involving some fixes. And the whole thing is very tricky. And I don't want to get into it too much because of time, and also it's a little bit inside baseball. But basically, you run into a few problems. So for example, this is one of these is an optimization. So like when you notice that the length is 0, you think that you can like actually check some of the recursion in the ABI decoder, but you actually can't because you need to check that some of the pointers are valid. And then there's other weird things where you're doing pointer arithmetic. So the user, if they provide some attacker payload, can force some like arithmetic overflow actually during decoding. So there's all these kind of like weird pointer things which can happen. And by the way, we fixed all these within 10 minutes. We fixed all these within one release cycle. So these were like, we like did some fixes, and then we like went through them and found some other issues. So eventually what we realized was that we actually need a spec. So we want to allow stuff like this, which users think is important or interesting, but we also want to basically avoid bad pointer behavior. And the way we defined it is, so here, this is not even a recursive thing, but this is recursive, right? So basically, the pointers are currently allowed to point anywhere. And as I mentioned with the call data, that's OK because the user controls all the data. So what we ended up deciding is that we allow these arbitrary weird pointers that aren't like necessarily pointing to contiguous things, but they have to be within the user-provided payload. So you can jump. So from this inside thing, you can maybe jump out here, you can jump up here, you can jump up here, but you can never jump out of it. And along the way, we kind of realized that this is impossible to like test, right? Which is why this is a fuzzing talk. So yes, so this is what we ended up deciding on, and I wonder why this slide is wrong. Is the slide wrong? No, it's not. Okay, so eventually we decided that in order to test this, we needed to write a simple implementation in Python. And this Python implementation is basically the spec. And the reason is that the compiler code for the ABI decoder is full of stuff like this. It's long, it's probably hundreds of lines, it's one of the most complicated parts of the compiler, and it does all kinds of weird optimizations for different cases. Because the code is so hot, it really does need to be fairly optimized. So what we did was we wrote a spec implementation, which is this, and it's here, and basically it's supposed to be as simple as possible. Maybe I'll pull it up if I have time at the end. And then we fuzz it. So we check that the spec implementation decodes data the same way that the compiler does. So we take the same data, we feed it to the spec implementation, and we also feed it to the compiler and see that they give the same result. Why is this actually interesting? The interesting thing is that doing this the naive way, where you just like feed random data to both of these implementations, doesn't really work. And the reason is that the input space is absolutely massive. Right? Like if you take that bytes example, that's like 128 bytes. That's like, I don't know, what, 8 to the 128 is the size of the input space. And also like any given pointer, which is something that could be a problem for us during decoding, is a uint 256. And that's like a huge thing. We could like run this until the heat death of the universe and never find a bug. And I just did this naturally because I think about the heat death of the universe all the time. So we noticed this, right? We started running the fuzzer, and we're like, it's not finding any bugs. And in fuzzing, like, you don't want to be like biasing the fuzzer too much. You don't want to be like, oh, we're not finding any bugs, so there must be something wrong with the fuzzer. But like, it should kind of be finding known bugs after some amount of time. And if you think about it conceptually, like, it's not going to find bugs. Like, if you just provide a string of random bytes to one of these things or whatever, it's just going to be trivially invalid, right? It's going to be a trivially invalid ABI payload. So there's a couple techniques we used. One is mutating valid data. So you take a valid ABI payload, and then you kind of point mutate it. Or you do something weird. You take a slice of 32 bytes and rewrite it into some other 32 bytes. Still weren't finding bugs. And the reason for this is that conceptually, when you think about the ABI decoder, when you think about it for long enough. I'm probably not in the first 5 minutes, but eventually you're like, gee whiz, the only hard things in the ABI decoder are actually these pointer dereferences, because everything else is straightforward. And a uint 256 is just like you copy 32 bytes. You can't get it wrong. When you decode the bytes, that's also just a copy. You can't really get it wrong. The only tricky thing is like ensuring that all the user pointers are valid. So we started doing something which I consider a little bit clever, which is kind of making the ABI payload as full of fucked up pointers as possible, like poison pointers. So we like bias the fuzzer heavily, or not that heavily, but a little bit, and this is actually the part of the fuzzer which does it, to, when you do the point mutations, to kind of draw from things that could be valid pointers, or they're like maybe just outside of the range of the valid space. And this is interesting because it introduces the concept of like high value data. So I think the kind of, yeah, so this is very interesting, right? So here's the important part. We take the, for the data that we're going to point mutate with, or like the word, you take it and it's kind of bounded by the length of the payload, and like anything in the range of like minus length of payload to length of payload times 2 or something is probably like a reasonably good thing, especially with like integer overflow. So this checks like all kinds of things. It checks out of bounds, overflow, off by ones. Yeah, I probably have like 3 minutes left. So I think the takeaway is that when you fuzz, you kind of want to have an idea of what values are high value, what things are high value, what things are poisonous to your program, and kind of try to guide your fuzzer towards those things. You don't want to do it too much because kind of the point of fuzzing is also to find bugs that you don't know about. But if you have some idea of what is poisonous to your program, then, which is funny because we're talking about snakes, Vyper, then you want to kind of bias your fuzzer a little bit with those. And here's our, in the interest of time, have to stop. Here's our GitHub, Telegram group. Any questions? No, actually. It's still running. Please.
So I missed, what fuzzing technology do you use?
Oh yeah, there's a library in Python called Hypothesis, and it basically lets you combine different strategies into larger strategies.
I don't know specifics, but I do know that AFL, which has dominated fuzzing for the past 12 years, supposedly had exactly this motivation to be really good at finding serialization bugs or bugs in big binary buffers as input. So I don't know if Hypothesis is AFL based, which is kind of the library that now many languages use for fuzzing. If it is, I'm a bit surprised, but I don't know enough, so maybe it's completely natural. Like you said, it's very hard to fuzz those things.
AFL is interesting because it's coverage based, right? And when we're fuzzing the compiler, what we're actually interested in is the coverage of the generated binary. And it's like not that easy to create coverage-based hooks for AFL for the EVM bytecode. Yeah. Okay.
Sorry, my bad. I just wanted to ask you if you have some thoughts on how you will improve the developer experience of generating custom mutators for fuzzing from your own experience.
Oh, that is a really interesting question because so if you see here, the mutation routine is kind of weird. You like draw from, the way I implemented it is you draw from like a list of possible actions, and then you apply those actions to the original payload. Like edit, add, delete, whatever word. That's actually really slow because the way that hypothesis works is it like creates some weird AST full of the possible actions and then it like traverses it. So it's like not, it doesn't really feel native. So I have a lot of thoughts about that, but maybe we can take it offline.
Thanks for that. Is there anything in particular you were using or techniques to identify whether the fuzzer was making progress? And
Yeah,
like,
that's a good question. Basically we would run it against like various commits and see if it found bugs, and it actually was pretty effective at that.
yeah. But say if it's running for a day, like there's no flame graph, or like, you know, if it's running for a day, it's always the problem of maybe if I just run it for a day +1, it'll find the thing.
Yeah, that's one of the things that's really hard to reason about with fuzzers, right? Is like, what kinds of inputs have you already done? It's really unintuitive. What kinds of inputs have you already tried? What kinds of inputs are you going to explore next? Like, what is the input space and how do you traverse it? So that is one thing I wish we had better visibility on. There's like debugging facilities in Hypothesis, which kind of let you inspect this, but it's really manual. It's not like an amazing, beautiful dashboard. Yeah. Okay, I think we're at time. Thanks.